We're going to talk today about trig identities. And some of the, just looking at an equation like 2x plus 3 equals 5, this equation is not true for all values of x. I mean, you would know to solve this, you would subtract 3, and then you would divide by 2. So it's only true for a certain value of x. Some equations have one solution, some equations have more than one solution, like quadratic equations. But what we're going to look at today is something called identities. And a trigonometric identities, what these are equations that are true for all values in the domain. And we've seen a couple of these already. We know that tangent theta is equal to sine theta over cosine theta. We know that cotangent theta is equal to cosine theta over sine theta. That would be true for all values in the domain. So remember that for tangent, if cosine theta equals 0, then tangent would be undefined. For cotangent theta, if sine theta equals 0, then cotangent's undefined. But for all other values of theta, these equations are true, and that's what makes them identities. We have some other identities that are called reciprocal identities, and we know that cosecant theta is equal to 1 over sine theta, and secant theta is 1 over cosine theta, cotangent theta is 1 over tangent theta. And again, those are for the values that are in the domain. For example, when sine theta is 0, then we know cosecant is undefined. So those are reciprocal identities. We are familiar with those already. What I want to talk to you now is about Pythagorean identities. Now, we remember from the unit circle, this is a unit circle because the radius of the circle is 1. So we have this unit circle, and I have a triangle marked in here, and so the horizontal distance here is x, the vertical distance is y, so I have this point on the unit circle. We also can see that we have a right triangle here, so using the Pythagorean theorem, we get x squared plus y squared equals 1 squared, or 1. So that's just the Pythagorean theorem. But remember that we defined cosine theta as adjacent over hypotenuse, so we got x over 1. So then we saw that x equals cosine theta. Remember from the unit circle, the x values were all the cosine values. And we know that sine theta is defined as opposite over hypotenuse, so we get y over 1. So we have y equals sine theta, which remember on the unit circle, all the y values of the ordered pairs were the sine values. So if I make that substitution, I get cosine theta quantity squared plus sine theta quantity squared equals 1. And this is called a Pythagorean identity. Now, typically we don't write cosine theta quantity squared that way. We actually write it as cosine squared theta plus sine squared theta equals 1. So when you see this written in that format, sine squared theta, just keep in mind what that means. It means sine theta quantity squared. It's just the notation we use. And generally, you won't see the cosine listed first. You'll actually see the Pythagorean identity listed this way. Sine squared theta plus cosine squared theta equals 1. And that's the Pythagorean identity. That's the most common. There's some others we're going to see in just a minute. You might see this in some additional ways. So you might see sine squared theta equals 1 minus cosine squared theta. Or you might see cosine squared theta equals 1 minus sine squared theta. But we're going to be looking at some other identities, and we will be referring to these. So there's some Pythagorean identities. All right, so here's a proof that we're going to do. We're going to prove this identity. Tangent square theta plus 1 equals secant square theta. So one of the techniques when you are trying to prove that something is an identity, remember, to prove something in math, we can't just substitute numbers in. We have to prove it with just variables. So the strategy is going to be, I'm going to start with just the more complicated side, which is the left-hand side. So I'm going to start with this tangent squared theta plus 1. Now, one good method for proving identities is to change tangent, put everything in terms of sine and cosine. So I'm going to change tangent squared theta to sine squared theta over cosine squared theta. and then I have plus 1. So now I need to add this fraction, this rational expression, to 1. So remember that the strategy we have for that is to find a common denominator. So I'm going to multiply the top and bottom by cosine squared theta. So when I do that, now I have sine squared theta plus cosine squared theta over my common denominator, which was cosine squared theta. Okay, so far I've started with tangent squared theta plus 1. Now here's where I am. Now I'm going to make use of what we just proved, and that was that sine squared theta plus cosine squared theta equals 1. So I'm going to replace that with a 1. Since I already have proved the other Pythagorean identity, then I can now make use of that. So now I get 1 over cosine squared theta, which, remember, 1 over cosine theta is secant theta, so this is just secant squared theta. And take a look at what we were trying to prove. We're there, so we're done. So this is a proof, and this is actually also a Pythagorean identity. There's actually 3 of them. The other one will relate cotangent squared theta to cosecant squared theta. And here we are. So I had this kind of listed as for you to try. So you can pause this and give it a try, see if you can do that. So if you want to try it on your own, go ahead and pause it and then start it up when you're done. Okay, so what I'm going to do is I'm going to start with the left-hand side. I'm going to start with cotangent square theta plus 1. I'm going to change this to cosine squared theta over sine squared theta plus 1. Find a common denominator. So I'm going to multiply this by sine squared theta over sine squared theta. So now I have cosine squared theta plus sine squared theta over my common denominator. Now, because addition is commutative, the order doesn't matter. So cosine squared theta plus sine squared theta is just 1. So I get 1 over sine squared theta, and that is just equal to cosecant squared theta, which is what I was trying to prove, and so we're done. So this is the third Pythagorean identity, and so that's important. We're going to use that when we are proving identities. Okay, so here we have a problem. Suppose that cosine theta equals -2/5, and theta is in between pi over 2 and pi, and we need to find the exact value of sine theta. Now, we've done these before. One of the reasons why it's in this section, I'm going to show you a different way. We've done this before building triangles, and you can continue to use the building triangles method. But remember that we now know that sine squared theta equals 1 minus cosine squared theta. So we have an alternate way of solving this problem. Now I still need to pay attention to the quadrant. So theta is in quadrant, if it's between pi over 2 and pi, theta is in quadrant 2. And I know in quadrant 2, sine is positive. So my answer is going to be positive. But now what I can do to solve for sine is I'm going to take 1 minus, and I'm going to square cosine, which was -2/5. So I get 1 minus, now when you square this, first of all, it's going to be positive if you square a negative. And with a fraction, just square the top, square the bottom. So you get 1 minus 4 over 25. Now if you find a common denominator, it's going to be 25 over 25. So when you subtract, you get 21 over 25. Now remember, that's sine squared theta. So to get sine theta, you take the square root of that. And I'm going to take the square root of the numerator and the square root of the denominator. So I get the square root of 21 over 5 for my answer. That's because, remember, sine theta is positive. Now, the alternate approach, you can still stick with this. Build your triangle. I'll call this theta. Here's my right angle. If cosine is 2/5, that's adjacent and hypotenuse. Remember, I'm not going to worry about the negative. I already know my answer is going to be positive. Use the Pythagorean theorem, which says 5 squared minus 2 squared, so I get 21. So this is the square root of 21. So that means sine theta, we already determined was positive, square root of 21 over 5. So you can continue to use the method you already know with triangles, or now we have this alternate approach. Okay, in this next problem, we're asked to simplify this trig expression, which looks pretty complicated. We've got tangent squared theta minus sine squared theta all over tangent squared theta times sine squared theta. Now, my strategy on this, when I have a fraction and it involves adding or subtracting in the numerator, I'm going to split this apart. So I'm going to say this is the same as tangent squared theta over tangent squared theta times sine squared theta minus sine squared theta over tangent squared theta sine squared theta. Hope you're good with fractions, because that's what you're going to need to do some of these. Hopefully you can kind of see where I'm going with this now, because the tangent squared thetas cancel. So I'm left with 1 over sine squared theta. Over here, the sine squared thetas cancel, reduced to 1. And I'm left with a tangent squared theta in the denominator. So over here I have 1 over sine squared theta, which is equal to cosecant squared theta, minus, and here I have 1 over tangent squared theta, which is equal to cotangent squared theta. Now if you check back at one of our identities, this one where we had cotangent squared theta plus 1 equals cosecant squared theta, I'm going to write that down and see if we can use that. We had cotangent squared theta plus 1 equals cosecant squared theta. So take a look here. Notice that if we rearrange this and change this to, if I subtract cotangent squared theta on each side, so now I can see that relationship here. So I can see that this actually simplifies to 1. And so how do I know I'm done? Well, I can't get much more simple than that. So this whole expression up here actually simplifies to 1. Okay, and here's another one, and I know it says practice, so you could give it a try, but let me just show you what I would do on this. So to simplify things, one good strategy is change everything to sine and cosine. Now the alpha and beta are 2 other commonly used Greek letters for angles. So if I want to just change everything to sine and cosine, this is all multiply. So cosecant is 1 over sine theta. Cosine theta, I'm just going to leave, but I'm going to change it to cosine, oh, I'm sorry, they're alphas, cosine alpha over 1. And tangent alpha, I'm going to change to sine alpha over cosine alpha. And this is all multiplying. So again, with fractions, I can simplify these cosine alphas to 1, simplify the sine alphas to 1, so this equals 1. And so now I know you're probably thinking, wow, everything in trig simplifies to 1. No, afraid not. So here are some strategies. If you are trying to simplify a trig expression, if you notice something squared, try to use a Pythagorean identity. It won't always work, but sometimes it does. If there's not anything squared, change everything to sine and cosine, because then sometimes you can cancel some things out. And if you have fractions, find common denominators and combine them, or if they're already combined, then you might want to break them apart. So those are some good strategies for simplifying trig expressions.